Hard task, it has to be really interesting. They only have 3 minutes, and we decided that it would be a lot more interesting to take one test case example and then try to work out what all the different engineers do that are on that project. So we're going to be looking at a really modern, advanced hospital and how that would be helped by all the different types of disciplines of engineering. So we're going to start with chemical and process engineering, and then after we've gone through all the disciplines, we're then going to have some people from industry come and tell you what on earth engineers do in real life. So I'm going to start it off with Matt Watson. Take it away.
All right. So the theme is Hospital of the Future, but before we get into that, I want to talk a little bit about what engineers do. So we are, as a group, we're problem solvers. And I think the major problem of our time, and your generation will experience this, is that there's going to be 10 billion souls on planet Earth by 2050. So you're going to be probably in your 50s at that time. You're going to be tomorrow's leaders. You're going to be the politicians, the industry leaders, the decision makers, and so on. And there's a lot of sort of issues associated with that. And I think that there's a huge opportunity for engineers in general to supply food for those 10 billion people, clean water, renewable energy, and so on. And I've put up some examples of how these challenges can become opportunities. Of course, they have a chemical engineering bent to them. But one of the aspects of having 10 billion people on Earth is that there's an increased expectation of healthcare. And most of us, at some point in our life, will see the inside of a hospital. So let's get right on to thinking about a hospital and what chemical engineers do. I'll challenge you to come up to me afterwards, and in fact you can try this with any of the engineers here, to name something that's in a hospital that an engineer has not touched. And I can get quite specific about how a chemical engineer would have touched every aspect that you're seeing. I guarantee that I can do it. But some examples that you might want to know about for chemical engineers is that the anesthetics that you might have, if you're undergoing surgery, would involve a chemical process and therefore involve a chemical engineer. The antibiotics that you have to keep you infection-free post-surgery are made with the input of a chemical engineer. The materials that are in here, like the coatings, the paints, and so on, those all involve chemical engineers. And then even stuff like the oxygen that often helps you breathe while you're under, that is heavily involves a chemical and process engineer. So let's just think about oxygen for a while. Oxygen is made by taking air, this sort of invisible stuff that's all around us, cooling it down so much that it actually starts to liquefy, and then distilling that liquid, which is a mixture of nitrogen and oxygen, to separate those two components. That liquid oxygen is then trucked around the country, and it's stored at the hospital. It's then vaporized as needed and then delivered to the patient. So that's just one example of how chemical engineers are involved in the hospital tomorrow. I'm going to hand it over now to colleague Matthew from Civil Engineering.
Kia ora koutou, nau mai haere mai, ko Matthew Hughes taku ingoa. Hello everyone, welcome. My name is Matthew Hughes. I'm a senior lecturer in disaster risk and resilience in civil and natural resources engineering. And I'm going to talk to you briefly about some of the civil engineering aspects that you might want to consider when you're designing and building the hospital of the future. And I want to use the hospital as a lens to try and understand the different disciplines within civil engineering that you may have the opportunity to study and to become those engineers. So here's a photo actually of what you could consider a hotel of the future. It's been recently built. It's actually Christchurch Women's Hospital. It's a state-of-the-art hospital. And one of the key disciplines that we need to have to build such an impressive structure is geotechnical engineering and geotechnical engineers. This requires having an insight into ground properties, ground conditions, rock strengths and soil strengths and things like this, to be able to properly design the foundations for such a large structure. Then we move to essentially the above ground part of the structure, where structural engineers really come to the fore. And so if you go into the discipline of structural engineering, you'll learn about all the material properties of the things you'll be using to construct these kinds of structures, how they behave under different stresses and loadings, all those fundamental things that you'll need to understand to keep the structure up and to keep it safe. Another unique aspect of our program here within civil engineering is our subdiscipline of fire engineering. And so if you are a bit of a pyromaniac yourself, you might want to indulge in this. But it's actually a very critical and important part of subdiscipline of structural engineering and materials engineering. So if you get to think carefully about the fire, you can try and understand its behaviour and how it might behave in a building, and therefore design the building from a material and structural perspective to keep it safe, and so it doesn't actually cause damage from fire or harm the occupants of the building. Another aspect of this is transport engineering, and so Christchurch here is a good example of this, where our hospital is essentially the nexus of these transportation networks within the city. And as transport engineers, you'll have an opportunity to help design transportation networks, think about different modes of transport, private vehicles, public transport, and cycling, and things like that. So it's quite an exciting opportunity to help actually determine the flow of people and goods around the city by concentrating on transport engineering. Another major focus that we can address here is earthquake or seismic engineering, and it probably won't be a surprise to you being here in Christchurch to know that this is a strong focus of what we do. What you're seeing there is a simulation of the actual earthquake shaking that occurred in the Christchurch earthquake on the 22nd of February 2011. And this is a very important series of experiences, and that's my cowbell. I'm not going to move very long. By the way, when you hear the cowbell, that means I've been speaking for too long. So we can design base isolation to protect buildings, and we can also use water network and water system engineering to provide safe drinking water systems, and it's another aspect of civil engineering that you can focus on. And just quickly, I just wanted to touch on something that we call humanitarian engineering, and this isn't unique to civil. It's thinking about appropriate technologies. It's thinking about human-centered design, and a range of civil and structural engineers and other things can contribute to this. But notice that all my pictures have been lacking something. They've been lacking people. And so really, I just want to emphasise in the concept of humanitarian engineering, it really is around the people that we're serving. So, by the way, you might want to try shaking that cowbell in lectures if the lecturer goes over time. I'll hand over now to natural resources engineering.
Okay, hey everyone. My name's Jane. I'm from the Natural Resources Engineering Department. So the first thing I want to do is just back right up, because constructing this hospital is going to have all sorts of different effects on the environment that we need to consider during construction. So basically we need to identify all these effects and come up with ways to reduce or remove their impact. So for instance, if civil says this hospital is going to have deep foundations, well, our drinking water comes from groundwater supplies underneath the city. So if we're digging deep foundation pits, that means that we're at risk of exposing those groundwater resources and contaminating our drinking water supply. So one of the things we might need to do is design some sort of system to pump all of the groundwater away from this area in the meantime. And the Avon River is right next to this hospital. The construction is going to generate all sorts of sediments and dust, and with many of the sites in Christchurch built on old landfills and industrial areas, it's not the kind of thing that we want to be going out into the river. So the site's going to need to be completely sealed off during construction, and we can put some sediment fencing along the side of the river as well to keep it safe. Once the hospital's built, there are lots of ways that we can help reduce its environmental footprint. One of these is the hospital's got a pretty large car park and a pretty large roof, and that means we're going to get all sorts of hydrocarbons from vehicles, heavy metals, suspended solids washing off into our stormwater drains every time it rains, which is not great news for the fish, plants, birds further downstream, not to mention in the Heathcote estuary and the ocean, where all of this stuff eventually ends up. But instead of putting in a big artificial filtration system, why don't we try and incorporate some of the environment's natural processes into a solution? Like stormwater, groundwater, which is filtered by rocks and soil, we can set up layers of stone, plant roots and soils to filter all those contaminants out of our stormwater before they get out to the main river. A few rain gardens would look great in the car park or a constructed wetland next to the hospital as well. If we're looking for a few other ideas to make our hospital look great and also reduce its environmental effects, well, how about a green roof or a green wall? These are a really cool innovation. So they attract birds, bees and butterflies to the central city, improving the urban diversity. Green walls also provide insulation, so they make for a warm hospital that's cool in summer and warm in the winter. And that groundwater beneath our feet, it's not just good as a drinking water supply. We can pump that up from the ground, run it through a heat exchanger, and use the energy we've extracted to run our air conditioning and our heating systems all year round. The best thing of all is that once we're finished with it, we can pump it straight back underground, making the whole operation essentially neutral. So while it seems more and more like our cities are just becoming industrialised concrete jungles, it does not have to be like this. Natural resources engineers are leading the charge, not just to protect the environment, but to make an integrated part of the way that we manage our cities, our buildings, and our roads. Thank you.
So I can keep going. So this is a really good example of how engineers are sometimes required to stretch their skills and their knowledge into other fields, which is exactly what I'm doing now. So I'd like to encourage you to think about the discipline of forest engineering. And so it's quite a complex and diverse field sometimes, but fundamentally it's around managing trees and the engineering processes around using wood products. So if you just look at the pictures there on the left-hand side, we have wood pellets for fuel, for burning, for heat and heat production and energy production. And this is using the byproducts of the wood processing industry. And I don't want to use the word waste, because in this context there's no such thing as waste. It's simply the feedstock for the next industrial process. In the middle there on the bottom, you can see that wood is actually a really important building material. It has been for many thousands of years. And is increasingly becoming a new building material for our modern buildings. We have ways of treating the timber and cross-laminating it to make it a very strong, versatile material that's very earthquake resilient as well. Another added bonus of using timber in modern structures is that it's a very efficient and a way of sequestering or locking up CO2 in the form of wood to try and address climate change. And finally, on the right-hand side, wood is aesthetically pleasing. It softens what otherwise might be quite cold and hard and clinical environments in a hospital. And finally, a major focus of forestry engineering is health and safety. And so trying to focus on that to try and prevent these new patients getting into our hospitals in the first place. So with that, we'll hand over to mechanical engineering.
All right, so I'm Debbie Monroe in mechanical. So mechanical engineering is basically anything that moves. So it cuts name from machines and mechanism. But we also are part of civil engineering in that we take care of the mechanical devices that go into a building, such as the heating, ventilation, and air conditioning systems. We're also involved with alternative energy, such as wind turbines and solar energy systems. And we make a lot of small mechanical devices, things with engines in them and robotics, as well as things that fly and all types of aerospace activities. Mechanical and aerospace are very closely linked. But the important thing to remember is that we can't do it alone. If you're interested in mechanical engineering, then you'll be working on the physical design of devices, and you'll need to partner with other closely related fields such as mechatronics and electrical engineering. In a hospital, we would be designing the equipment. So all of the beds, the medical trolleys, the blood pressure cuffs would involve a mechanical engineer. And like others have pointed out, pretty much every device in a hospital includes a mechanical engineer on the team. We also make the majority of the medical devices. So if you are in the field of orthopedics, you design the orthopedic implants, as well as the external bracing and systems that go with that. We make devices that monitor glucose levels and provide insulin, either ones that pierce the skin like this, or patches that have microarrays of needles that you can't feel. And there's an important subdiscipline in biomaterials that makes printed heart valves or patches for the heart that can be made out of specific biocompatible materials. How am I doing? 3 minutes?
20 seconds.
Oh, 20 seconds to go. So now I switch badges, right? Okay. Hi, I'm Debbie, and I'm representing mechatronics engineering. So, mechatronics engineering is engineering that makes smart systems. So if you have a mechanical device and you want to add intelligence to it, then mechatronics is a good field for you. It combines mechanical design with computing and electronics, and as you can see the cute little animatronic robot in the center of that diagram. But it covers hovercraft, all the sensors and electronics in your car, and any type of control systems that make rockets fly and robots run. In a hospital, you'll find mechatronics everywhere. We have medical devices, the sensors, the actuators, the computation that goes into those is a mechatronic device. We have lots of robotics for rehabilitation, such as exoskeletons and artificial limbs, as well as assistive devices. And then there's all kinds of monitoring systems that would fall under mechatronics engineering, including sensors, computational, and health monitoring systems. Some of the emerging applications in mechatronics are quite exciting in hospitals, such as robotics for surgery. The device in the middle and left at the top are hopefully you'll never have to have one of these, but it's to do stitching inside of the bowel. On the right is a company called Robodoc, and it is used to do robotics preparation for hip replacement surgery. And then another area of mechatronics is in prosthetics. So we have prosthetics that can work off the electrical signal in the muscle to provide an amputee with a replacement limb, such as an arm or a leg.
Okay, so now we have an empty building, potentially, that's dark. We've got lots of cool toys, but none of them work, or they don't do a lot. So what do we need? What do we still need? Well, we need electricity. And certainly the hospital of the future will probably be even more electrical than the hospitals are now. We need energy, and just think about how would you supply energy to the hospital of the future. Funnily, Christchurch Hospital is actually getting one of these biomass energy systems, so that's not the future, it's already happening now. They're replacing their coal power plant with one of these biomass power plants. But you could go all the way. You could go to the other example. This is a hospital they built in Haiti after the disaster in Haiti. That's completely solar powered. Can we build our future hospitals so they're completely solar powered?
would be a good thing. I mean, in an earthquake, you could lose your network, your power distribution network. What do? Well, we could also go, and I challenge you guys to look into this area, is we could have giant batteries. Giant batteries could power our hospitals. So this is a really amazing new technology. You can have flow batteries, where the size of the battery really just increases with the amount of chemical that you can store in a liquid form. So we're not talking about your lithium-ion batteries, but we can build megawatt power systems now that could battery power a whole hospital. So we have power. If we have all that power and all that electricity in these buildings, we need to figure out how we make it safe. Patients in the hospital are usually in a state where they don't want to experience current flowing through them. So one of the major design aspects that people don't think about in hospitals is that how we make them electrically safe. And that's a really interesting area for engineers to go into. Lastly, well, you know, the future. Let's think about some ideas of what we could do. Currently, our medicine is based on an average person. What if you could do personalized medicine? And that's certainly something that electrical engineers could help with sensors and actuators. So you can imagine that a hospital in the future has an automated line, as you can see in that picture here, where they would make drugs deliberately just tailored to your own personal medical history or your genetics. That's something that's currently very difficult and very expensive, but if you have automation, you can actually test a person, test their genetic composition, and actually make drugs that are specific to a person. In the same way, and we've already seen some of this, you know, a lot of the things that happen in a hospital could happen at home. And this is what we call either implants or personalized medicine, point of care, where you can do a lot of the things that you have to do in the hospital now, you can actually do at home by yourself. And again, all these implants, they need to be powered and they need to be safe to use. So that's what we do as electrical engineers. I'll stop here in terms of power and I'll hand on to computer engineering, because none of these things will work very well unless they have some software that runs on that hardware.
Good evening, everyone. I'm Steve, I'm the Director of Studies for Computer Engineering, and I want to give you a brief overview about a hospital of the future with computers. So, one device that basically is being developed at this university, and there's been major contributions from electrical and computer engineering, is, for example, the Medipix scanner, or Mars scanner, which is a Medipix all-resolution scanner. And this is where we have 3D X-rays in colour. Some of you probably have seen examples of this on television, where you put a foot into the scanner and you can actually see different slices. Now, on the right, there's basically a picture of the scanner and what it's going to look like. And the idea is that hopefully they're going to be made cheap enough so that they can be all over hospitals and even eventually in doctor's surgeries. So basically they can actually do all these imaging, basically for patients on demand. Now, everything inside that box on the right, okay, is basically powered by a computer. There are the scanners, for example, that are actually doing the scannings. They actually come from CERN, which is a nuclear research organisation in Europe. Now, what drives them, or what actually uses the information coming off these scanners, is a computer. All right, so there'll be some form of either a microcontroller, a field programmable gate array, a number of different networks. In fact, you've got these heterogeneous systems, computer systems, that are basically inside the box. So it might not look very, technical as far as the outside is concerned. It looks very sort of modernish type thing, but inside it, it is incredibly complex. So the design of these systems is what computer engineers do. Also, patient care is an incredibly important part, of course, of any modern hospital. And so there'll be a plethora of different types of instrumentation. And every box that you see in that picture on the left-hand side, and also the ones at the bottom of the overhead here, are powered by not one, not two, but multiple controllers or microcontrollers. The networking that actually does all of the systems control is part of the Internet of Things, and that's also part of computer engineering. So there's also a term called interoperability, where you do basically it's a plug and play with different types of systems. Again, that's a big part of computer engineering. And lastly, but certainly not least, is systems that are actually happening outside of the hospital environment. So you'll have patients at home, for example, and they'll be monitored by physicians through devices such as lab-on-chips. So the lab-on-chips on the bottom right-hand side of this slide shows, for example, how you can actually have in vitro control of a patient, and one would be monitoring glucose levels, for example, and that's all happening in real time. Information is then being fed back to experts in the field who can then monitor what's going on. So all of these systems are based on basically computers, okay, and the networking of computers and the systems integration is a huge part of that. Thank you.
I'm going to hand on to Matthias.
Okay, so my name is Matthias, I'm from software engineering, and we already heard that in order to make a hospital work, we need, I think, electricity, power, we need computers, but we also need software. So this is where software engineering comes in. It's about building high-quality software that actually powers the hospital, or let's say that powers our smart hospital. So essentially it's about digitalizing all the processes we have in the hospital, about digitalizing the services and the devices. And software engineering is kind of a cross-cutting discipline because we have seen a lot of, or we have already heard a lot about devices, smart devices, about computers, computing, and so on. And usually these devices, they use software. The software makes them actually function. And the question is, how do we build high-quality software that doesn't crash, that can actually be maintained, and so on. So, yeah, software engineering is kind of multidisciplinary. We would use knowledge from other engineering disciplines, but we would also need to have an understanding of computing principles, programming, networking, human-computer interaction, AI, depending on what type of application you actually implement. And a lot of the work we do is actually, almost all of it is not done by individuals, but we do them as a team, and there's a lot of creativity involved to build kind of a delightful experience to the patients of the hospital rather than having a very frustrating experience when you go to our engineered smart hospital. So, if you think about a smart hospital, I mean, on the left we have a hospital and we have a bunch of departments. So as a software engineer, we would look into these departments and try to figure out how can we support them, what kind of software can we develop. We may have some software to analyze lab samples, we have some software to process the admission of patients, to help schedule appointments, for example, but also we need to have some operating theater management software and so on. But the real interesting stuff starts once we start looking beyond the boundaries of the hospital. So if we want our hospital to also communicate with other healthcare providers or insurance companies or first responders, so how can we actually make this happen? How can we make this happen in a secure way, reliable way? And one example would be the electronic health record. So how can we build a record of patient data that can be accessed from anywhere by all sorts of players in the healthcare market, but still make sure that the data is actually reliable, secure, that we make sure that its privacy is not breached and so on. We heard about the Internet of Things before, so, well, this is also where software engineering comes in, because we can have all these smart devices, but the question is, like, how can we make sure, or how can we make sure that the devices communicate with each other well? How can we make sure they collect data properly, that they analyze data properly? So think about rehabilitation, physical rehabilitation. So you as a patient, you may have some sensors, and you would like your sensors communicate with your smartwatch and with your smartphone, and you also would like to upload your health status to the internet or website. So how can you actually do that? So there's a lot of software involved. Telemedicine, we saw this as well. So how can we build telemedicine in a reliable way that it doesn't crash when the doctor communicates with a patient somewhere overseas or in far distance? So there are a lot of types of software we can actually develop. Now, what are some of the challenges? So again, I think just like the first speaker I need to calm down. Okay, so how can we, just to take a lens on software engineering, just like I think the first speaker did it as well. So what kind of challenges would we face? Well, the first one is, what are the actual end users, what are the customers we're going to build the software for? They may use different devices, they may actually have different needs. Then how can we make sure we trust the hospital or the software that we deploy in the hospital? We want it to be fast, we want it to be reliable, accurate, so how can we actually achieve this? It's not just sitting down and hacking something together, but it's actually applying some systematic engineering principles and practices. And yeah, last but not least, how do we handle the complexity? So it's not usually hospital software, it's not about hundreds of lines of code or 1,000 lines of code that we write, but millions. So how do we handle this complexity, and how do we make sure that if we have a bug somewhere in the system, we don't have to shut down the rest of the system? So now I think I really have to go. So I'm keen to talk more about this, so if you have questions, I'd be happy to chat with you after. So.
Okay, for a start, I think we need to thank the academics. Do you know how hard it is for us to speak in under 50 minutes? So if you could join me in thanking them for giving it a good go. And it was quite a big challenge because we constrained them to the hospital scenario just so you can try to see the different types of engineering and what they do. Now, I have been told we have a couple of recent grads who may be willing to talk to us. Is Alida here? Yes, awesome, cool. So basically, rather than us telling you what to do, because some of you may not want to become a professor, I don't understand it, but that's true. We thought we might get some people from the real world, so please come on up and tell us a little bit about what you do as an environmental consultant. Have I got that right? Awesome.
Hi, my name is Alida. I studied chemical process engineering, but ended up as an environmental engineer. So they took on 3 grades in my year. One was civil, one was natural resources, and one was chemical and processing. That was me. They may tell you that I forced them, but we made good friends. So it's quite, when I was studying chemical process engineering, I never thought I'd end up as an environmental engineer, but there's so many applications of chemical and processing in the treatment of wastewater, stormwater, drinking water, and I also do some air dispersion modelling. So as a consultant, I guess we do a lot of monitoring and testing, and then we use that data to design a system which we give to a contractor who hopefully doesn't say, guys, this is impossible to build, please get some practical skills. That pretty much sums up consultancy to a team, and yeah.
And we've also got Stephanie here, awesome, who is a site engineer. Fantastic.
Hey guys, I'm Steph. I'm a civil engineer, but I work as a site engineer for Downer. So going into engineering, didn't again really know what I wanted to do, but I thought building a bridge would be pretty cool. So down the civil way I went, and then I found out structures was really hard and not really for me. So I went down the waterway, and then I got a job as a contractor. So we're the ones that actually do the building and tell the consultants literally all the time that they're stupid and that's actually not practical. Honestly, every day. Sometimes you're like, I've told you already, it doesn't work. So that's actually a really fun part about my job. I quite enjoy that little win. So now I'm actually building roads, which again, never thought I'd be doing, but I love it. The cool thing about being on site is you're actually there, you're the ones that are working with the diggers, trying not to get hit by them, and all that fun stuff. So my job's to take the design, first of all check that it works, as it often doesn't, and then put it practically and build it. One thing I really like about civil engineering is right now I'm building a new motorway out by Rolleston, really cool, go drive past. And it actually encompasses heaps of different types of civil engineering, so we do all the water stuff, put all the new stormwater pipes, wastewater, all that kind of stuff. We do the environmental stuff, we build roads, we build bridges, we even put in like traffic signs because they've got to have a little foundation in them and everything. So that's why contracting is really fun. Also, you get to, another thing I like is you kind of get to deal with the money side of it as well, which is something I was always a little bit interested in, and deal with how you're going to win over and make some sweet money in it. So that's why we've done the site engineering way, so contracting for the win.
Very good, thank you very much. One of the things, I get asked a lot of questions about life as an academic, in the real world. I'm just not going to win that one. Okay, there's so many things I was told as an engineering student about being an engineer. For a start, I was told, but you have people skills, why are you studying engineering? Engineers don't have people skills. Wrong. Okay. There's a lot of people work. Now, if you don't like people, it's okay. We can probably find a safe cubicle for you. That is still an option. But for the rest of you that actually don't mind interacting with people and like working on teams and like creating something huger and bigger than you could achieve yourself, then there's lots of opportunities for you. If you want to be outside, then there are site visits you can go on. There's things you can do outside. If you like being in an open plan office, does anyone like that? There are opportunities for that, but there's also opportunities where you could be in an office by yourself. There's opportunities where you can work at a keyboard. There's opportunities where you could be in a lab. So basically it's up to you creating the job you want. If you decide that you don't love engineering, it hurts. But there are other options as well. I've had some of my students then go on into finance. Finance love engineering thinking because we're teaching you a way of thinking. So one thing you may have heard in the last two speakers we have is it's okay if you don't totally know what you do, and it's okay if you don't actually end up doing the discipline that's probably the perfect discipline for you. I know so many people that did engineering with me that are now working in a different type of engineering. So it's a way of teaching you thinking, so don't stress if you don't get the choice and you decide it's not the perfect choice. When you get out there and you've got engineering thinking, you can move into other areas as an engineer. Now I was told that Nick might have a few things he wanted to say about life in the real world, because academics are a great source of information on such things.
I haven't always been an academic. So I worked in industry for 15 years before coming to New Zealand. I grew up in New Zealand, but I lived in the States for about 22 years. And I worked primarily in research and development roles for a large industrial gases company that was based in North America. And that gave me opportunities to literally travel the world. I could take as much travel as I wanted. After a while I got sick of it, but I got to spend time in lovely places like Vancouver, Canada. I got to visit people in Brazil, Japan, Korea, China, France. I could go on. And there's a long list there. I also had the opportunity to work on some very large capital projects. So these are multi-million-dollar builds of things. I built an enormous combustion lamp, a furnace that was about 10 meters long, 3 meters in diameter, and you could throw about 6 megawatts of flame into it. That flame is about 10 meters long. And I used to play with fire for about 6 years when I was paid to do it. A lot of fun. So you have a combustion facility here. It's a good one. It's not as big as the one I got to play on, but it's a fun thing to do. I played around with really high temperature materials for quite some time. And then towards the end of my career at the industrial gases company, I led a team of about 20 people, 10 in Pennsylvania, on the east coast of the US, and another 10 on the west coast of the US. And so I had opportunities to go into management for about 2 or 3 years as well. So I had a pretty broad kind of brushstrokes look at, and working with lots of other engineers, technologists, business people, marketeers, finance, and so on and so forth. It's been quite a useful career.
As you're seeing, everyone's loving the engineering. It's awesome. Did Derek have something he wanted to say as well? No, the moment's passed. It's okay, yeah. Cool. So we've got a few other things for you. Now, the reason we do it at this time of year is not to torment you, and we know you've got lots of assessment. I'm really sorry. It's because you're having to start thinking about what you're going to take in semester 2. And the courses that you take in semester 2 then decide what you're open to doing in your first professional year. So you don't have to decide what your first professional year is yet, but you do need to decide which courses you want to do in semester 2, and the student advisors are available to help you. We've also got a handout here that you can pick up at the end. So rather than me guessing what you want to know, I've got all these amazing people that I can call up onto stage at will. Awesome. So do we have any questions? So if you have a good question, and I don't mean a silly question, but a genuine question, then I have chocolate that I can give you for your question. They've given me a lot of chocolate. There's heaps of chocolate here. So does anybody have a question? Oh, here's the chocolate. So if we've got questions, he wants to give away chocolate. Excellent. We have a taker at the back. that's a really good question. What GPA do you need to take whatever discipline you want? I think is it still a B for guaranteed? It's usually much lower than that. Should I say that? Yeah, it is. I had a look last year, because I said at the beginning of this year, I'm like, how many people did not get the discipline of their choice? And it was a reasonably small number. So if you pass all your courses and you work hard, then you've got a good chance of getting the discipline you want. Now, occasionally we will have a situation where everybody wants to do a certain discipline, and our labs just can't take it. So every now and again, we will have the GPA go up higher for a specific discipline because everybody was just really loving that. So I don't know which of these people gave the best presentation, but that might be where the problem is next year. So you can sort of guess that one.
But aim for about GPA 5.
Yeah, a GPA of 5 is good idea.
Which engineering discipline, when they come out of their degree, who's like most employable? Like, what's the percentage rate of who, you know? Yeah,
Okay. Right. Okay, fight time. Who's gonna? Okay, who thinks that they are the most employable? 100%. I'm not going to get a sensible answer out of these people. Seriously, we need all the different types of engineering out there, so it's really hard to choose. So my recommendation is to choose the type of engineering where going to work is fun and play and it's not a chore. There are some that do pay a little better than others, but bottom line, you want to be going to work and enjoying yourself. He's got a lot of chocolate there.
Well, which one does pay the most?
Oh, I don't know. Does anybody know which one pays the best? I mean, civil and software would be right up there, wouldn't they? Computers up there too.
Software.
The power industry, electric was going to say power industry does really well. Petrol, again, they're not going to help me out here. So you can find high-paying jobs in all of them. Engineering is a really good field to get into. Who else wants dessert? Yeah, good plan. It's very hard to switch disciplines if you get too far through your degree, because if we look at the first professional, it's all compulsory courses. They all start in first semester. So it does get messy. We have had people switch disciplines, but it generally means you're going to be here for more than 4 years. If you've done some STAR math and stuff, you might have some spare space and you might be able to work it out, but it gets very, very difficult. If you're in those first 2 weeks and you work out, I've made a wrong error, then if that program is not at capacity, then there may be that opportunity of switching, but the further through you go, you really have to retake all the courses, so it does take more time. But what I was referring to was the fact that once you're out in industry, you're not stuck in mechanical engineering. You can find employers that will help you grow into other areas. And we saw with our industry speakers that they'd actually ended up doing something quite different than what they've studied. And a lot of our final year projects are very multidisciplinary. So mechanical, mechatronics, electrical, because I'm in that space, I'm sorry, I'm sure it's the same for the others. We all work together on the same project, so you can learn a lot of skills in that one.
At what point in the year do we have to choose our first pro this year?
Oh, I don't have the date. Do you have a date?
1st of December.
1st of December. Yeah, and please submit the application in time. When I was checking with the student advisors at the beginning of this year how many people didn't get their degree of choice, specialisation of choice, it said, well, the biggest problem was they didn't apply in time. So I know it's hard after the exams to think about all that stuff, but try to put that ranking in first, and then, yeah.
In terms of like career paths, what are the pros and cons of being in a more general degree like electronics rather than specialising in either mechanical or software or electrical?
Oh, that's an interesting question. I don't know if everyone heard that. but it was talking about mechatronics being the more general degree and mechanical and electrical as more specialised. And that's interesting because we thought mechatronics wasn't specialised and mechanical and electrical were the generalist. So this is what it comes down to. New Zealand degrees are quite broad by nature. So if you went over to America and you did an engineering degree, it would be very, very narrow. And the reason for that is that they have enormous companies that you can do just one tiny little thing your entire career. In New Zealand, we have small and medium enterprise, so small companies, medium companies, and so you generally have to be able to do quite a range of tasks. So our degrees as well are quite broad. So that first professional year will be quite broad. So for example, in electrical engineering, it goes anything from power systems right through to doing software programming, and that's all in one degree.
What sort of additional specializations or variations of the current ones are looking at being added in the next few years?
Oh, I might get Debbie to come up and say that. So do you know a specialisation that might be being added in the future?
So we're starting some new minors. There's a couple that exist in chemical and process engineering. I'll get their names wrong. Energy and bioprocess. Okay, so those exist already, and you can look online and find out what the requirements are for those. And there's some in electrical too. I think power. Yeah. So in mechanical, we are starting a new one in biomedical engineering. So that's launching this next year, assuming we get QF approval, which I think we will. And it's a 5-course, so 75-point specialization. It's the same as a full mechanical engineering degree, but it has an additional competency in biomedical engineering. And then for mechatronics students, they'll be able to take it as a stream, so it won't show up as an official minor on their transcript, but within the next couple of years, it'll be a minor for mechatronics as well.
Thank you very much. Another thing I'm just going to do is you may not have heard about the humanitarian engineering, so I'm going to ask Matthew if you can come up and say something about that.
Where's the cowbell? So I am the co-director, along with my colleague Ricardo Bella Mendoza, of the Humanitarian Engineering Program. And so at the moment we have available an undergraduate diploma in global humanitarian engineering. One of the rationales for developing the program is to give you the opportunity to broaden your skills, your communication skills, and your understanding of the humanities and how people work, how communities work, and combine that with some practical field engineering and experiences working with communities in New Zealand and overseas. So essentially, if you've got a taste for adventure and travel, this is one way that you could explore that. We've had students do design summits through Engineers Without Borders and going to various countries in the Asia Pacific region where they stay with communities and work on engineering projects. It might be water projects or energy or combinations of those things. We are, however, in addition to that, going to have a much broader focus here in Aotearoa, New Zealand, and partnering with our iwi communities, marae, around the country, and really trying to partner with them to give you the opportunity to work with developing communities. The emphasis being that there's a lot of development to be done around the world, and actually at the start of tonight's session we learnt the world that you're going to be moving into when you're getting older and you're leaders, where there are going to be billions of more people around the planet. The pressure on resources is going to be severe and extreme. Many of those billions of people are going to be living in cities that haven't been built yet. And having an accreditation and a passion for humanitarian engineering can really give you some more insight into how we can start to deal with these issues, both engineering issues and wider socio-cultural and socio-economic issues. Practically what the program involves is that you do your Bachelor of Engineering Honours, And over the time, or you can also knock off some of the papers over in summer, or you can spend extra time on your degree to do some humanities papers. And we have a schedule of papers that you can do. If you want to learn another language, that can be really useful, string to your bow around that as well. And we have final engineering capstone experiences around field engineering, which means you get practical experience in digging bores and using pumps to establish water sources, and as I said, a culminating experience working with communities. Thanks.
Thank you very much. We also have minors for the computer engineering students in communications and networking, and there's a minor for electrical engineering students in power. So do we have any other questions? Anybody else who wants some chocolate for dessert? Oh, we've got one up here.
One of your speakers said that she started civil and went to natural resource, I think she said. So those two are easier to switch between, and maybe some of the other might jump between those.
Who wants to speak that? Do you want to come and speak about that?
Sure. Yeah, so the first professional year for civil and natural resources is exactly the same. So it's only in second pro that they actually kind of start to diverge, and civil's doing structural sort of papers while natural resources is going off and doing like ecological engineering and catchment management and that sort of thing. So you've kind of got another year to, like, if you really, really wanted to change, then you can probably speak very nicely to the department and they might let you. Yeah, if you got the grades, of course. We won't leave internet reads otherwise. Awesome. Okay, anybody else got some questions? Yeah, cool. Matthew, when do you have to apply for humanitarian engineering? How do they get into that?
To apply for the humanitarian engineering program, it's available on your MyUC. It's one of the options if you go through to the college options there. Come and speak to me afterwards though, and maybe we can catch up another time and I can talk you through it. But you can basically start at any time.
Awesome. It's not too late. So many opportunities. Any other questions? Awesome.
Will we get a chance to try out the different disciplines in our courses this year?
Okay, we'll get a chance. I believe some of the engineering papers, they try to give you a wee taste of the different disciplines. You'll get some more presentations. In Term 3, we're going to be doing lab tours. In Term 4, then you get to have a look at all the third pro projects and see what the actual fourth year students have been doing with their discipline of engineering. Does anybody else have anything they want to add about that from the intermediate?
Engineering 101.
Engineering 101, yeah.
Yeah, there's those presentations. There's also some labs.
So some of the labs are also available. I can think of the famous bridge one for the civil engineers. On the 28th of May, at the far end of the Cape Wing, in the parking lot out there, there's a fluids lab where the students compete to find out who has the best fluids project. So those are always good for a laugh. There's probably others as well for each of the disciplines.
So you don't get to do so much of tasting all the disciplines in intermediate, but we do try to at least tell you what they're all about. It's also talking to people, so after this, go up and talk to these people one-on-one and find out a little bit more. Do come to the lab tours in Term 3, because then you can talk to the actual students and the actual people in the department and see what they're doing day to day. The clubs, yes.
And the clubs are open to everyone, so they can...
So clubs such as like the Formula SAE would be a chance of trying some of the types of engineering. I think the Shell Eco Challenge would be another one. You've got a biomedical club. There's the electrical engineering club as well. So there's quite a few different clubs around where it gives you a chance to see what's going on. Okay, so this is again for you, Matthew. You're going to be a busy man. So it's what types of engineering disciplines are most suited to humanitarian engineering, and the other part of it was job opportunities.
all disciplines. Correct answer. But that is true. In the past, there's been this perception of it's kind of a civil natural resources thing because of establishing water sources and things like that. But I'm really intrigued by the whole biomedical devices and applications. The use of technologies, software, electrical and otherwise, to support remote and rural communities, for example. That's all humanitarian engineering. And we just really need to broaden our minds about what it is. So it's everything. So what was the second question? Job opportunities. There are specific agencies you can work for. I'm thinking UN agencies. You can work in the development field, disaster response. Many consulting firms and big engineering firms have arms within them that do this kind of work, working with communities. But also just having this skill set of understanding people and communities and the contexts in which engineering occurs is just an extremely valuable skill to have, full stop. And it can, so with your, as an engineer, you know how to do things. As a humanitarian engineer, you know how to ask the question, should we and can we do it differently? And so that can only be better for you as a person and for your employment opportunities.
Very well said. So my specialisation is telecommunications, so cellular technology, and in 2020 we'll be rolling out 5G, that's coming a little bit early. And there the whole design has been faster, more data, it's all been technical. With 6G we're starting to design that for 2030, and the number one focus is how is this going to affect society and how is this going to help people. So this is a change that's coming in engineering, is that we've got to think beyond the technical and we've got to actually think about the impact we're having on society, because it's rather large and as engineers we can do a lot of good or not. Okay, any other quick questions? Okay, what I'm going to suggest now is that we actually give you a chance to come and talk to some of these people. It's a really good chance to ask them a little bit. I'm going to ask these people, if nobody's coming up and talk to you, then go and meet some of our wonderful first year students. And they may say, no, I want the other discipline, but you might find some interesting things out of that anyway. So thank you very much for making the effort to come tonight. I hope it's been useful, and very good luck with your exams coming up. Thank you. Another thing, we've still got some sandwiches and stuff left, so for any of you that aren't at halls and could do with some lunch tomorrow and can't be bothered making it, go for it.